Hey there, everybody. Sorry I cannot be in class. As I said in my email, everybody at my house is sick. So, what are you going to do? So, let me just sort of quickly move through some of the material I'd wanted to do today. Today is an introduction to our last unit, which is modeling with SIR models or SIR type models. So, the point of this video here is to give a global overview of these models without telling you what they are, just talking about what they're used for, how we'll be using them. So just a bit of history here. These models date back to the 1920s by Kermack and McKendrick. So they have this really nice paper from the 20s that was the first time anybody had tried to do mathematical epidemiology using math to study the spread of disease. And here's an image from their original paper. This is modeling the outbreak of a disease in a city in India, and I can't remember which one. Now, if we were in class, we would play a guessing game, and I would ask you to guess what disease was being modeled here. This is a 1927 paper. The disease they were modeling, this is an outbreak from 1905 and 1906. And the disease was the plague, which is not usually guessed, a very old-timey disease. But this was an outbreak of the plague, and the black curve is what their model predicts, and the scatter plot points are what actually happened. So, of course, it's not a perfect fit. Models generally aren't perfect fits, but it's a pretty good fit. So these models are meant to model the spread of disease, but not any disease. So there are lots of different diseases out there. Some of them do not spread in any meaningful sense. So SIR models, what are they designed to do? They are designed to model diseases that are contagious via human-to-human contact. So something like malaria perhaps is contagious in some sense, but it's spread through mosquitoes. And certainly not cancer, which is not contagious at all, as far as I'm aware. And also diseases that are recoverable. So you have the disease for some amount of time, and once you've recovered, you're immune at least for a while. So we're not talking about HIV here, which certainly is contagious via human-to-human contact, but HIV is not recoverable in this sense. So you should be thinking things like the common cold, flu, chickenpox, whooping cough, Ebola, SARS, COVID, all things like this. SIR can try to model those things for you. For diseases like these, like the flu, the population can be divided into three groups: people that have the disease currently, those who have had it, and those who don't yet have it but might get it. Those are the three populations of interest. So people who are capable of spreading the disease right now, people that had the disease, so they have recovered, and we'll talk about this later, but recovered can actually mean multiple things. It can, among other things, mean you've died, which is not usually how we think of being recovered. But from the model's perspective, a dead person can't spread the disease, so they count as recovered. It could also be somebody who is inoculated, so you've recovered that way. And those who are susceptible. Those are the three populations of interest. So these models work by building a differential equation for each of the three population groups. So we get a system of differential equations, and then you have to solve the system to make predictions about how the disease spread. In order to actually get a given model up and running, to model a flu outbreak or a COVID-19 outbreak, you need to know a few things, but not many. You need to know the number of people initially infected. This is usually very small. You usually start at the beginning of an outbreak. How long the disease lasts in a given sick person on average. So different people last different amount of time, but you just want an average number there. And some measure of contagiousness. If you have those three things, you can set up an SIR model. Now, if I go back to this slide, one reaction you might have is, wow, the 1920s were a long time ago. That's before computers, before the Instagram and things like this. All the things you youths are into today. This predates all of that. So a good question to ask is, something from the 1920s, is that still useful? Because, of course, math and technology have come a long way. And the answer is, yeah, they actually are still pretty useful. Maybe not the classical ones all the time, but certainly SIR type models are very useful. So they've proven to be surprisingly robust, and they certainly aren't maybe the best tool for like the CDC to use. They'll use some fairly sophisticated statistical models that we can't get into, but people at the CDC certainly do still look at SIR models, and they're pretty good tools. In particular, they can help provide information about like a best case, worst case scenario. So they're good for that. Now, again, if you're worried about relevance, I did a Google Scholar search for this. Not just any disease, but COVID-19 SIR model. And I asked it to look just last year and this year. And there were more than 13,000 results. So these are still very much being used, still very much relevant. So again, this is not like a classroom exercise or a historical exercise, right? We're not thinking about, hey, back in the day, what did people do? In contrast to what people do now. These are still used quite a bit nowadays. So that's a global overview of SIR models. It's a system of differential equations that are set up to model disease outbreaks for diseases like COVID-19, the flu, mumps, and things like that. Now in the next video, I'll actually show you the models, but this is a global overview here.